Hello everyone. Today we're going to talk about nucleus of an atom. The nucleus of an atom is the central region of an atom where the majority of the mass is concentrated. Through the scattering of alpha particles experiment by Rutherford, we learned that the nucleus of an atom contains a majority of mass of an atom. Numerically speaking, the nucleus of an atom occupies almost 10 raised to the power minus 14 times the volume of the atom, but contains 99.9% of the atomic mass. The nucleus of an atom is so small that if you expand an atom to fill up a room, the nucleus of an atom would still be no larger than a pinhead. Nuclear composition. Atomic nuclei are built of protons and neutrons. Nucleus of hydrogen atoms contain only single proton. Charge on a proton is 1.6 into 10 raised to the power minus 19 coulomb, and its mass is 1836 times greater than that of an electron. Neutrons are uncharged particles, and mass of a neutron is slightly greater than that of a proton. Neutrons and protons are jointly called nucleons. Number of protons in nuclei of an element is equal to the number of electrons in neutral atom of that element. All nuclei of a given element does not have equal number of neutrons. For example, 99.9% of hydrogen nuclei contain only one proton. Some contain one proton and one neutron, and a very little fraction contains one proton and two neutrons. Elements that have same number of protons but differ in number of neutrons in their nucleons are called as isotopes. Hydrogen isotope deuterium is stable, but deuterium is radioactive, and it decays to changes into an isotope of helium. Isobars and isotones. Nuclei with same A but different Z are known as isobars. For example, 40K19 and 40Ca20 share same mass number 40 but differs in 1 unit of Z. Although isobaric atoms share same mass number, but they differ slightly in their masses. This is very slight difference in masses of isobaric atoms is related to difference between energies of two atoms, since small mass difference corresponds to considerable amount of difference in energies. Nuclei with same number of neutrons but different number of protons are called as isotones. For example, 198Hg 80 and 198Au 79. Size of nucleus. First estimate of size of nucleus was provided by Rutherford scattering experiment. This scattering experiment we have already discussed. In Rutherford scattering experiment, incident alpha particles get deflected by target nucleus as long as the distance approached by the alpha particle does not exceed 10 raised to the power minus 14 m, and Coulomb's law remains consistent. Apart from Rutherford scattering experiment, various other experiments like fast electrons and neutron scattering experiments were performed to determine the nuclear dimensions. Since electrons interact with nucleus only through electric forces, so electron scattering experiment gives information on distribution of charge in the nucleus. A neutron interacts with nucleus through nuclear forces. So neutron scattering provides information on distribution of nuclear matter. It was found that the volume of a nucleus is directly proportional to the number of nucleons it contains, which is its mass number A. If R is the nuclear radius, then the relationship between R and A is given by R equals to R naught A raised to the power 1 by 3, where R0 is equivalent to 1.2 into 10 raised to the power minus 50, that is equivalent to 1.2 FM and is known as nuclear radius parameter. Binding energy. During the 20th century, the popular Albert Einstein came up with the revolutionary theory, the theory of relativity. The theory explained that mass and energy are inconvertible. The mass cannot be converted into energy, and vice versa. This new dimension to physics helped to resolve plenty of unsolved problems and formed a forum for lot new theories. One among them is the existence of nuclear binding energy, thereby giving a clear sight into nuclear mass and internuclear interaction. This is when a small nucleus of a smaller mass plus binding energy, it gets separated nucleons of smaller mass. Mass defect. An atom comprises of a nucleus at the center and electrons revolving around it in an orbital fashion. Nuclei constitutes of protons and neutrons, combinedly called nucleons. Thus, we expect that the mass of the nucleons will be same as the sum of individual masses of neutrons and protons. But it is not true. The total mass of nucleons is less than that the sum of individual masses of neutrons and protons, which in fact constitutes it. This difference in the mass is called mass defect, which is given by delta M equals to Z into M raised to the base P plus A minus Z into M raised to the base N minus M into N U C to the base, where ZMP is the total mass of the proton. A minus Z into Mn is the total mass of the neutrons, and MnUc is the mass of nucleus. According to Einstein's theory of relativity, the mass energy are equivalent. That is, the mass of the system measures the total energy of the system, given by the famous equation E equals to mc square. Hence, it is implied that the total energy of the nucleus is less than the sum of energies of the individual protons and neutrons, which implies that when nucleus disintegrates into constituent nucleons, releasing some energy in the form of heat energy, the energy emitted here is mathematically expressed using E equals to delta M into C square. Now imagine the situation of breaking the nucleus. To attain this, a certain amount of energy is required to put into the system. The amount of energy required to achieve this is called as the nuclear binding energy. Thus, we can define nuclear binding energy as the minimum energy required to separate nucleons into its constituent protons and neutrons, and is given by E to the base B delta M into C square. Thus, the difference in the mass is converted into nuclear binding energy. How to calculate binding energy? By the following steps we may understand. Once the mass defect is known, the nuclear binding energy can be calculated by converting that mass to energy using the formula e to the base b equals to delta m into c square. We have to make sure that the mass is in the unit of kgs. Once the energy obtained is known, it can be scaled into per nucleon and per mole quantities. Nuclear binding energy curve. This is the graph which is showing nuclear binding energy curve. It is having nuclear binding energy in mega electrovolts per nucleon as the function of number of nucleons in the nucleus. Notice that iron 56 has the most binding energy per nucleon, making it the most stable nucleus. The rationale for the peak in binding energy is the interplay between the coulombic repulsion of the protons in the nucleus, because like charges repel each other, and strong nuclear force or strong force is what holds protons and neutrons together at short distances. As the size of the nucleus increases, the strong nuclear force is only felt between nucleons that are close together, while the coulombic repulsion continues to be felt throughout the nucleus. This leads to instability and hence radioactivity and fissile nature of heavier elements. To calculate the average binding energy per mole of uranium-235 isotope, we have to show the answer in kilojoules per mole. First, we are going to calculate the mass defect. Then later on, we are going to find out MD, that is nothing but 1.86564 AMU, that is atomic mass unit. Then we will be calculating the mass in kgs. After we have calculated, we calculate the energy by using E equals to mc square. After E has been found, that is in joules, but if you want to find it in kilojoule per mole, we are going to convert it and we are going to find out the answer. Radioactive decay. Radioactivity is the phenomena exhibited by the nuclei of an atom as a result of nuclear instability. Henry Becquerel discovered this phenomenon. It is a process by which the nucleus of an unstable atom loses energy by emitting radiation. In a drawer which was having photographic plates, a small amount of uranium compound was wrapped in black paper and was kept in it. Examination of these plates later resulted that there has been an exposure. This phenomena came to be known as radioactive decay. The radioactive elements are the elements or isotopes which emits radiation and undergoes the process of radioactivity. The atom particles cannot be bounded because there is no energy due to the presence of an unstable nucleus in the element's radioisotope. There is a constant decay in the isotope in order to stabilize itself with a release of a lot of energy in the form of radiations. Transmutation is referred to this process of isotope transforming into an element of a stable nucleus. It can occur both in natural or artificial ways. This is the diagram showing radioactive decay, where alpha particles have been emitted. Alpha decay is a type of radioactive decay in which the atomic nucleus emits an alpha particle, thereby transforming or decaying into a new atomic nucleus. Here, the atomic mass number of the newly formed atom will be reduced by 4 and the atomic number will be reduced by 2. The emitted alpha particle is also known as helium nucleus. The mass of alpha particles is relatively large and has a positive charge. Ernst Rutherford distinguished alpha decay from other forms of radiation by studying deflection of radiation through a magnetic field. The deflection of alpha particle would be a positive charge as the particles have positive 2e charge. Following is the equation of alpha decay. AXZ, we get a daughter plus alpha particles. A is the total number of nucleons. Z is the total number of protons. Alpha decay symbol is denoted by alpha or helium plus A2, positive. What actually happens in alpha decay? Alpha decay occurs in very heavy elements like uranium, thorium, radium. They are called parent nucleus and are basically unstable. Because the nuclei of these atoms have a lot more neutrons in their nuclei than the protons, that is, they have too large a proton to neutron ratio, which makes these elements neutron rich. The richness makes alpha decay possible, thus emitting its 2 protons and 2 neutrons in the form of an alpha particle and forming a new daughter nucleus, and attains a very stable configuration. Alpha decay can be described like the nucleus of these nuclei, that is the parent nucleus, rich atoms split into 2 parts. The alpha particle goes zooming off into space. The nucleus, that is the daughter nucleus left behind, has its atomic number reduced by 2 and mass number reduced by 4. We have the alpha decay equation for uranium-238-92. We get thorium plus alpha particles. A parent nucleus gets daughter nucleus plus emitted alpha particles. A parent nucleus and a daughter nucleus both are combination of protons and neutrons. Thank you.